So there's two final synthesis of amine procedures that we want to talk about, and these are actually going to both be rearrangement reactions that end up removing a carbon from a molecule. So the first one that we're going to talk about is the Hofmann rearrangement. Okay, and so what happens in the Hofmann is that you start off with primary amide. So primary meaning that there's no other functional groups, no other organic groups on the nitrogen of the amide. So it has to be NH2. And what you're going to do here is treat this with sodium hydroxide as base, and then bromine, okay, Br2, and then this is all going to be in the context of water, usually, okay? What's going to happen here is that you actually remove the carbonyl, so that gets lost as CO2, and you end up attaching this R group directly to the nitrogen. Okay, it's the Hofmann rearrangement. And you can see then that synthetically what this does is it allows you to take a carboxylic acid or some derivative, make a primary amide, and then remove the carbonyl. So whatever your R group was attached to the carboxylic acid derivative, that now becomes attached to the nitrogen directly. So it's a very useful and clever way to synthesize amines. So how exactly does this work? Okay, well, first off, we have our primary amide, and what's going to happen in the first step is that the hydroxide is just going to deprotonate that amide. Okay, so we're going to get to the anion of the amide there. Okay, and then that's going to react with the Br2. So we're just going to brominate the amide nitrogen. Okay. All right. Now in the second step, or the next bit here, we're going to use hydroxide again to deprotonate, and of course this is going to be much more acidic now at this point because of that Br group, but that then deprotonates and gives you the following anion. Okay, and now we could draw a resonance form of this intermediate, which might be helpful. So we'll just push that anion up into resonance with the carbonyl. Okay, so there's just two resonance forms. They're identical. At this point, we're ready to do something that that's akin to what we saw in some previous rearrangements. So keep in mind here that we've got this nitrogen-bromine situation, which really isn't very stable. And so this molecule sort of wants a way to deal with this instability. So what's going to happen is that the O- is going to kick down, and it's going to allow the migration of this R group. So this R group with its electrons in that bond are going to migrate over and kick out the Br minus. Okay, so it's going to inject Br minus. And so if you just add up where all of those arrows are pushing, we're forming a CO double bond, we're retaining the CN double bond, and we're attaching that R group to nitrogen. So what you get out of that is this functionality. Okay, so we just kicked off Br minus, and we get to this. So this is actually known as an isocyanate. Isocyanate. And conceptually, you can think about it as being a monoimine of carbon dioxide, right? So carbon dioxide would be just the two CO double bonds, and so we have a monoimine of carbon dioxide. Okay, now usually what's going to happen at this point, so isocyanates can be stable. You can actually buy a huge number of these things. They're actually very useful. But usually we're going to be in water, and so what's going to happen in that case is that we'll actually just hydrolyze this. Okay, so we'll go to the carbamic acid. Okay, carbamic acid, right? And that's that same intermediate that we saw in the last video where we were deprotecting carbamates. Okay, so we have a carbamic acid, and then this is just going to lose CO2 and give us our amine. Okay, so we take the amide, we deprotonate, and then add a Br, and that's what's going to be the trigger for this whole rearrangement. Okay, So we're going to deprotonate, and then that sort of initiates the transfer, the migration of that R group onto the nitrogen. And then afterwards, it's just the hydrolysis and decarboxylation of the isocyanate. Okay, so we can look at just a few examples of this happening. So let's say that we had this primary amide, okay, and if we just do a Hofmann rearrangement, so Br2, sodium hydroxide, and water, and this is pretty easy just in terms of predict the product, because all you have to do is remove the carbonyl and then attach the amine where that carbonyl was, right? So that's the Hofmann rearrangement product of that primary amide. And this also works with aromatics or other things. So here we have benzamide, okay, and we'll do the exact same conditions there. And what this will give us is, right, so remove the carbonyl, attach the nitrogen, that gives us aniline, okay? Now, one thing I want to point out is that we don't necessarily have to do this in water, okay? So if we were to do this same reaction, so I have Br2, but let's say then I was in sodium methoxide as my base, and so in methanol. What I will do initially is go to that same isocyanate intermediate. Okay, so in this case we have phenyl that migrated, but then this isn't going to hydrolyze with water, it's going to hydrolyze with methanol, and so we'll actually get out the methyl carbamate. Okay, so you see that, so methanol will add, and then that can't decarboxylate because it's a carbamate ester. So depending on the exact conditions, you might actually get the carbamate, or in theory, I mean, you could do it without any nucleophilic solvent. You could isolate the isocyanate, and then you could add a lot of different nucleophiles to that intermediate. Okay, so that's the Hofmann rearrangement. Very, very useful. And there's one sort of related type of reaction. This is what's known as the Curttius rearrangement. Okay, and so what we're doing in this case is we're going to so typically we're starting from the acid chloride. I'm sure that there are probably other ways to do this, but our goal here is to actually get to an acyl azide. Okay, so this is an acyl azide. Okay, and what happens in this case is all you need to do is heat. You heat this up and it'll happen spontaneously. And then again, we're typically going to do this in water, but that's something that can also be different. And this will also excise the carbonyl and give you the amine. So again, that R group ends up bonded to the nitrogen, and we lose CO2, and we also lose N2. And so how is this one working? Okay, so in this case, let's draw out the acyl azide. Okay. And so we've got a positive charge there and negative there. Okay, so it, formally it has these, this sort of ylid type of character, but overall it's a neutral molecule. Okay, so what we're going to do is, right, so this nitrogen has two lone pairs, that's why it's negatively charged. So if we heat this up, we can draw a resonance form where we're actually going to push electrons in the following fashion. So yeah, this is just a resonance form. There's nothing actually happening just yet. Okay, but this is a very, very important resonance form because you can see here that by doing that, we have N2 that's just dying to act as a leaving group. Okay, so that's very important, and honestly, we should draw that other resonance form as well. Okay, just like we did with the Hofmann rearrangement, we really should just draw this resonance form where we let that the lone pair on this nitrogen resonate up as well. So let's just go ahead and do that. And so now, do you see that we have the exactly analogous situation that we did in the Hofmann rearrangement? So the only difference here is instead of being Br minus as the leaving group, we have N2 as the leaving group. And both of those are very potent in terms of leaving groups. And so kick down, and then we're going to migrate over onto that nitrogen, and then that allows us to kick off N2. And so again, what we access here is the isocyanate, okay, and then we will have lost our N2 gas. Off that goes. And then of course, if we're in water, we are going to go ahead and hydrolyze and decarboxylate that isocyanate, and that's how we get to that amine piece. So they're very much related. It's just that the only difference here is sort of how we're accessing that key intermediate that allows the rearrangement to happen. And so I just wanted to show one real world example of a Curttius. Real world. Okay. And so this is actually used to synthesize an important molecule. And so our acid chloride that we use here is this cyclopropane. And so we treat this with, first off, sodium azide. Okay, that forms the acyl azide. And then the second case, we're going to add heat, and then we're going to do that with water around. And so that's going to affect the Curttius rearrangement. And so what we will get out here is, remove that carbonyl, and we will get to the amine there, right? So we just popped in the amine where that carboxyl group was. And this molecule is called tranylcypramine, which is an antidepressant. Okay, so that's an actual drug molecule that's used as an antidepressant. And just strategically, trying to make this cyclopropane with an amino group hanging off directly is very, very challenging. But it turns out that making that kind of cyclopropane with a carboxylate derivative is relatively easy. So the Curttius rearrangement allows you to do relatively easy chemistry, and then at the end convert that carboxylate into an amino group. So that's one of the reasons why this is so very useful.